Yeah, so today we've got Jason Hoelscher-Obermaier, ML research engineer, background in experimental quantum physics, joining us to present his summer research from PIBBSS 2023. And the title is How LLM Evaluations Reduce slash Influence AI Risk. So I'll turn it over to Jason. Thanks for being here with us today. And yep.
Yeah, thanks a lot for the introduction and thanks for coming. Um, I'll be very brief about myself because I think almost most people in the audience I have met personally. So as you said, my background is in physics. I worked in ML engineering for a while and then worked for the past year on AI safety research topics. Among those specifically evaluations. And that was also what I focused on during PIBBSS over the summer, where I worked with Clem and other people at ACS in Prague. And this is what this talk is about, even though it goes a bit beyond what I've been doing over the summer, because as should be the case, the time at PIBBSS has influenced my thinking and so I think the questions that I started with are not the ones that I'm most interested in now anymore. But they are all related to evaluations. So to give a bit of context, when we started the project, my research idea or the guiding question was whether we could use multi-LLM agent setups to study language model risks or specific language model failure modes in a way that is potentially more automatable and maybe even more automatable than the existing evaluations for extreme risks, which also rely a lot on like manual red teaming. So they require a lot of human labor and maybe also gives insights into risks or failure modes that are not as obvious. This turns out to be, I think, quite hard. And over the time of the PIBBSS fellowship, I've started to think that we just need to understand what we want to achieve with language model evaluations much better and what actually makes for a good evaluation. And this is what this talk is going to be about. So here are the guiding questions, and the goal for this talk is to hopefully give you some ideas about these questions. And for me, if you have good questions or good insights, to get your comments and feedback so that we can continue to think about this together. The first is, how do language models contribute to AI risks? Then what are the main types of language model evaluations? Here I'll give some examples that I've been working on. And then finally, how these evaluations actually influence AI risks. And that connects to what we want these evaluations to look like. So starting out, I want to say that I think that there are two main questions related to evaluations. One is a methodological question. That's the question whether the evaluation that we're performing is actually measuring the property that we're interested in. And the other one is a question of the theory of impact, which is that if we learn about the property of an AI model or a language model in this case, what actually happens as a consequence of that. So for language model evaluations, X, the property we care about might be any of the following, or actually might fall into any of the following categories. It might be a dangerous capability of a model. It might be a misalignment property. It might be a bias. It might be other things. And we have to ask, how can we actually measure this in a reliable way? That's the methodology question. And then if we're able to perform this evaluation in a reliable way, what actually happens? Can we then mitigate the associated risks? That would be the positive scenario. Or maybe what kind of risks are actually associated with the evaluation per se. So could this information then be misused, or do we in other ways increase the risk if we actually perform these evaluations? Okay, so first, how language models contribute to AI risks. I'm gonna divide this roughly into two broad categories. So on the one hand side, left on the screen here is the classic duality of misuse risk and accident risk, which in the AI case morphs into misuse and misalignment. So the misuse risk is all the things that can go wrong when a malicious agent or malicious actor uses uses a model to cause harm. Misalignment risks are the risks that happen from a model performing in ways that aren't intended by its users or developers. And both of these to actually cause significant harm, in both of these scenarios, we would require some form of dangerous capability. That's more an implicit definition of dangerous capability than any substantial statement. That's why I put this into quotes, because we can turn this around and say that a dangerous capability is whatever enables a malicious actor or a rogue AI to cause great harm. One thing that I find interesting and that kind of is a unifying thing for these two categories of risks is that they just increase with capabilities. So we know that for current frontier models and for the current training methods, we can't really target very well what kind of capabilities the models actually end up acquiring. And so we have to assume that for broadly capable models, like the current frontier models, further increases in capabilities also are like directly correlated with further increases in dangerous capabilities, and therefore increases in misuse and misalignment risks. And that's, I think, the current position that also the major labs are assuming, as is reflected in their so-called responsible scaling policies. So what are examples of these dangerous capabilities? The most commonly talked about ones are cyber offense. I think this is fairly understandable. It's the natural domain for language models. They live on computers. So it's the thing that they have direct access to. Deception and manipulation, which could be an important factor if language models interact massively with like lots of humans. And then weapons design, which can be a problem for both misuse and misalignment, like the other two as well. Then there is a whole other category of risks, which I think I'm not exhausting here, but I think the maybe most important examples would be risks from bias and prejudice. So this is things that can go wrong if the model, let's say, we say differentially discriminates against a specific social group. Then hallucinations and inaccuracies, things that can go wrong when you rely on a model, but the model just doesn't actually know what it's doing. And the most complicated structural risks, which are risks that actually depend much more on the deployment context than any intrinsic property of the model. To give an example there, let's think about a model that is broadly capable, but doesn't actually have dangerous capabilities, but maybe it's capable enough to actually contribute significant to economic activity. So it's introduced on a very large scale, driven by lots of VC money, and suddenly our economy is full of like these language model agents performing economic actions, but they, other than regular human economic actors, are just highly correlated in some way that this may be hidden to us. Maybe they all derive from the same foundation model, and this hidden correlation leads to largely increased fragility of the resulting economics. Let's say you end up with like a much higher incidence of economic crashes because of that. I mean, this is not a very clear story, but just like a rough idea of what kind of things we're thinking about in this category. What I find interesting about this right-hand column here is that in contrast to the left-hand side, it's not as straightforwardly clear what kind of relation it has to the scaling of capabilities. So if we imagine fixing the level of AI deployment at a given level, so let's say we have n language models in operation or kind of acting in our economy, and we increase the capabilities of these, then it's not straightforward to say whether these risk categories will grow or diminish. You could plausibly expect that bias and prejudice might actually become less of a problem if the model becomes more capable. Similarly, for hallucinations and inaccuracies, for structural risks, I don't even know what to say. Like, would depend so much on the exact scenario. So that's in difference to the left-hand column, where even if you fix the level of AI deployment, the risk actually goes up if capabilities increase. However, I think even on the right-hand side, there is still a strong argument to be made that also these kind of risks will become more important over time as models scale, because the increasing capabilities of models just also leads to much more deployment of AIs. So even if like the dependency on capabilities per se is not straightforwardly positive or negative, there's likely still a large contribution from the correlation between capabilities and the level of AI deployment. Next, I want to talk about LLM evaluations. The most important question, of course, is what you actually want to measure. And that is a question that we have not fully answered yet, because we haven't fully, I think, exhausted the risk scenarios that we are interested in. But then if you have found one thing that you want to focus on, then there's a couple of methodological questions around how you design your evaluation. And I want to just walk through a non-exhaustive list of different qualities these evaluations might have, and where you have to make some choices. So the first, and I think an important question, is whether you want to perform a model level or a system level evaluation, where model level means that you're somehow just looking at the properties of the bare language model, whereas the system level evaluation would also assume a certain scaffolding or a certain deployment context. For example, the model might have access to a code interpreter or a knowledge base, or it might actually interact with humans in certain ways. And that's like one of the first questions I think you need to ask, whether you can get away with a model level evaluation, or whether you need to actually consider the deployment context and somehow model and test that as well. Then there's the question whether you can perform your evaluation in an automated way, or whether you actually need human oversight or human assistance. There's the question whether you want to design a purely behavioral evaluation where you treat the model as a black box, or whether you can actually gain additional insight by also engaging in some mechanistic interpretability and actually looking at what is happening inside the model as it basically runs through your test. And there's a big question whether your goal is better served by an adversarial or a non-adversarial evaluation, where the adversarial case would be what people do when they do red teaming, Oh, I saw that there is something in the chat. I hope I haven't. Oh, okay, that's an old message. And the non-adversarial case is more looking at, let's say, an average case behavior of the model. But these technicalities aside, I think the important open questions for language model evaluations are kind of well captured in this quote from the what has now morphed into, I think, the UK Safety Institute or AI Safety Institute. They have published a large document on processes for frontier AI safety with recommendations, also around language model evaluations. And they write in that document that for many relevant properties of models, there do not yet exist accepted evaluation methods. And it remains unclear how reliable or predictive the current evaluation methods are. So I think this kind of sums up quite well the currently most fruitful research directions. One is to look at the properties of models that we're interested in from a risk perspective, where we don't even have a clue how to evaluate them. And then the second is like the methodological question: how reliable, how predictive, how robust these evaluations actually are. Okay, I'm going to switch gears now and talk about two concrete examples that I've worked on over the summer, so that we have something a bit more specific to discuss. One example is an evaluation for ethical behavior of AI agents that was published this year. This so basically the question that the authors here are trying to answer is: do AI agents still behave ethically when ethical behavior might be at odds with their goals? And the approach they take is to define a number of metrics for ethical behavior. They call this morality, power aversion, and utility, where morality is a measure of how often the agent violates a set of deontological principles. Utility is a measure of how often the agent causes disutility to other agents, independently of whether this is against some deontological principle. And power aversion measures how often the agent acquires instrumental power during its actions. And finally, they also look at a reward score, which is not ethically motivated, but just measures how well the agent achieves the assigned goals. The way they measure this is to work with so-called choose-your-own-adventure games. These games are can be conceptualized as graphs, where at each node you have a game situation, so that's a state of the world. That situation is described and defined by a textual description that the agent sees or that the agent gets as an input. And for each node, so for each state of the world, you have a couple of available actions. These are the edges in this graph, where each edge is also defined by a possible action, again, given in textual form and presented to the agent as a possible choice. Then every edge here is annotated with a bunch of labels that measure the reward that the agent acquires if it chooses that action, as well as any of the ethical metrics that have been defined before. So violations of deontological principles or disutility cost or power acquired. And then they basically just create a huge data set of choose your own adventure games and set a couple of agents in these environments and then measure their average performance across all these games, which then gives you the radar plot that I've shown before. That's supposed to tell you about the kind of trade-offs between different goals and reward maximization for different types of machine learning systems. So the question we have to ask now is, are we actually measuring what we're supposed to measure? So is this actually a reasonable way of estimating whether a language model agent would perform ethically in the real world? And I say no, even though this is a pretty good start, but it's very clearly still lacking for at least two reasons. One is that this kind of design of this benchmark assumes that the agent is always presented with an exhaustive list of actions. And what we're doing here is basically, if we're assuming that this is about testing the ethics of the agents, we're testing more its capability of evaluating a given list of actions than its ability to generate an ethical action from scratch. And of course, like the ethical generation is what we actually need because the agent will be performing in an open world scenario. Even more problematic aspect is that when you look into these games, they're of course meant to entertain and not to imitate the real world. So they, for example, contain assumptions about magic that the agent can perform, that it will not be able to perform in the real world, and that will also pretty clearly indicate to the agent that it's not in a real world deployment context, but it's actually in a game setup. So the relation of any scores that this agent achieves on these kind of games to ethical actions it would take in the real world is pretty questionable. It would at least need a pretty thorough analysis to know what we can actually take from this. The second example for an evaluation that I want to present is one I've been working on with two other PIBBSS fellows, Matthew Lutz and Janvita Modak, and Quentin, an independent researcher. It's a benchmark which we call Turing mirror, and this is not about ethical actions, but about a different capability of models, which is whether language models can actually recognize their own output. And a second related question, whether they could exhibit a systematic tendency to prefer their own output. The second question is the one that I think is maybe, the first question is pretty interesting, I think, from a interpretability point of view. The second question is interesting from a structural risk perspective. So if there was like a strong systematic preference for language models for their own output, I think that would imply that we need to think very closely about, or very thoroughly about, what happens if you put lots of these in interaction. Maybe there is like network effects happening that we don't actually want to happen if you have this kind of systematic preference of agents for output of their own kin, so to say. So how did we go about creating that benchmark? We wanted to have a relatively clean data set where we are sure that the AI is not able to kind of deduce the let's say the source of the text from the content. So we went with a data set called Understanding Fables, which comes from the Big Bench set of evaluation data sets. It consists of 189 human-written fables that come together with a human-written moral. Originally, this data set was created to test text understanding of AIs, but we basically extend this data set in a way that it becomes suitable to answer our questions about text attribution and text preference of language models. And how we do that is we basically create an aligned corpus of human-written fables and AI-written fables by taking the human-written moral and then asking different language models to write a short fable, a fable that matches the length of the human fable, whose moral is whatever the moral is. And we do this for every row in the original data set. So what we end up with is an extended data set that has the human written moral, the human written fable, and then a fable with the same moral written by, let's say, GPT-3, another one with the same moral written by GPT-4, one with the same moral written by Claude, and that's that whole thing 189 times. And we can then use this data set to test for like the ability of LLMs to recognize their own outputs in contrast to output from other sources, or test the preference of the model for its own output versus output from other sources. Here's an example on what such a fable looks like. This one was generated by GPT-4. It's not important to read it in full, but short story is, I think it reads pretty convincingly, and it's not entirely clear which one, if you read this next to a human fable, this is not clear which one is the AI fable and which one is the human one. It also has to be said that the data set that we worked with was actually created on purpose to basically make sure that human fables don't directly correspond to anything that has been seen before by the model. So the generation process for the original data set was take human editors and basically modify existing fables until all of their obvious characteristics are changed. So the animals involved are changed. The story setting is modified such that it's not recognizable directly as a fable from one of the classic fables. To evaluate text attribution, we then take pairs of fables for the same moral. So fables that have roughly the same content, but maybe have a slightly different style, and present them to a model in context, and ask the model to give us our best guess, give us its best guess for which of the fables was written by an AI. We ask the model to return the answer in a JSON structure so that we can easily extract it. This works very reliably and very easily. And we also make sure that we switch around the fables. So we test every test case twice with the fables in both orders, because there is a quite strong order bias. If you don't do that, then you will have like very, your results will be very much off. Here is what we get if we do this. On the y-axis, you see different categories of comparisons. So on top, you see a comparison where a model was asked to judge which one is an AI-generated fable in comparison of a GPT-3 or GPT-3.5 fable compared to a human fable. Below that, you have the same for a Claude 2 fable versus a human fable, and on the bottom for a GPT-4 fable compared to a human fable. And the different colors encode the models that we ask to predict the origin of the fable. The turquoise bar is at 0.5, so that's like a random performance if the model gets it wrong every second time. And what we see here is that for some pairings and for some models, there is actually a pretty strong systematic effect. So the most obvious one is that GPT 3.5 is almost perfect at telling its own output apart from a human fable, whereas GPT-4 has a strong anti-correlation. So it almost always or very often attributes a human generated fable as the AI generated one. Whereas for other comparisons, it's not so clear. So specifically GPT-4 versus human seems to be quite a bit harder to tell apart for the AI models. The interesting thing is that we actually don't have a clue how the model does this. And the effect is pretty strong. So I think it will be robust. And I think if we repeat this experiment with other domains, I would predict that we will find similar, maybe not quite as strong, but I think we will still find similar correlations. And we actually don't know what the model relies on to identify its own output. When I say the model here, then I mean the GPT 3.5 model that is very successful at attributing its own text. When it comes to evaluating text preference, we use this prompt here. We again take pairs of fables. We again permute the order to get rid of order bias. And we just ask the model which one it thinks is better without really specifying what better means here. This again works quite well, even though I have to preface that when I show the next slide, we haven't run this on the full data set, so the exact numbers might still change a bit, but I think the results are directionally correct. And again, the interesting thing is that there is a pretty strong systematic preference. So what I'm plotting here is what I call normalized preference. On the x-axis here are different generators, so different sources of fables. And for each source, we basically measure how much this source is preferred to other sources, any of the other sources, where a normalized preference of 1 means that it's on average as likely to be preferred as to not be preferred. So that is like the random baseline. And a preference of larger than 1 means that it's actually systematically preferred. And again, the interesting finding here is that across different predictor models, so if you ask different language models for their preferences, the GPT 3.5 text was systematically preferred, whereas GPT-4 and human produced text is pretty strongly discriminated against in this test. And there's a slight discrimination against the Claude 2 text. Again, the interesting question is where this actually comes from. We don't know this yet. And it's something that I would like to look into further. So I hope that we will continue this research and extend it. We definitely need to extend it. There are some very clear limitations of this, and they kind of mirror the generic limitations of many of our evaluations, I would say. The first one is that it's pretty unclear how far these findings would generalize. And in particular, it's very unclear whether they would generalize to circumstances that we actually care about. So this is in a way similar to my criticism of the Machiavelli benchmark. And it's a criticism that can be leveled against most evaluations, that it's very hard to actually test in exactly the context that you care about. So in our case, if we care about preferential attachment of AI nodes to each other inside an AI-dominated economy, it's not quite clear to me what kind of test data set we would have to design to actually test for a systematic preference in that context. Another question is also one that can be basically asked with respect to almost every existing language model evaluation. How robust is this with respect to changes in the prompts? Something that one would need to investigate, and that we don't have, I think, a clear systematic methodology for doing. And then the final one is the one that I've been talking about already. What is actually the underlying mechanism? So if we find something like this, we would like to actually understand a bit more how this comes about. This would also give us confidence that we're not observing something spurious. but we don't actually know that yet. Okay, let's change gears once more. Let's quickly talk about how evaluations influence AI risks. So one of them I've hinted at before. Now in the wake of the AI Safety Summit, or just before that, most of the major labs have announced so-called responsible scaling policies, or OpenAI calls it risk-informed development policies, which basically define risk levels for given models and then define safety checkpoints, let's say, that need to be achieved before a new model can be a model of a given risk level can be developed. And these risk levels must somehow be operationalized. And the current thinking is to define evaluations for that. So Anthropic, for example, defines an AI safety level of 2 for a model that doesn't increase misuse risk, that has like dangerous capabilities to some extent, but doesn't increase misuse risk beyond that, what is achievable with like textbooks and a search engine. Whereas level 3 or AI safety level 3 would be a model that has the same dangerous capability, but is so capable that it somehow enables a malicious actor much, much beyond this current baseline. And to do that, they will need to kind of define an evaluation, a certain metric for dangerous capability in weapons design, let's say, and then define thresholds that correspond to the different AI safety levels. So without evaluations, we cannot do that. The second way in which it will influence future development is that it increases common knowledge about AI capabilities. This could be good or bad. I think it's probably mostly good, but it's a thing that one should be keeping in mind before publishing something. But I think the EA or how do you say, EA-related AI safety community is probably pretty aware of that already. The next, it's kind of tied to the first point, that also on the side of nation states or international bodies, evaluations will be a necessary component for defining AI regulation. Then there is an influence of evaluations on our shared sense of security. This could be either good or bad. So I think arguments can be made for, let's say, evaluations instilling a false sense of security. If you end up with, I don't know, a kind of a greenwashing of AI models by a regulator that says, okay, this is a safe model because it has passed these 10 evaluations, that could be very misleading, which could be quite bad. The final one is a bit harder to argue, maybe, which I would call a risk of crowding out unknown unknowns. It's pretty much related to the previous point. So if you end up operationalizing all the risks, maybe you get all the people just working on implementing evaluations, and not enough people worrying about things that the evaluations might miss. I'm pretty close to the end, so bear with me. But these are a couple of desiderata I think we would have for evaluations. When we want, so assuming that we have found, or assuming that we agree that evaluations are a good idea in principle, given or subject to the caveats from before about info hazards and around the framing of the evaluations to not give a false sense of security. then I think we would want to aim for a pretty broad coverage of risks. We want them to be roughly forward-looking, which I find pretty hard to define, but should mean something like they should be relevant for risks in a world that is about to appear and not only in what we are in right now. Then they should be robust to deception, which at the moment is still maybe a somewhat esoteric concern, but could become relevant sooner than we like, which means that we should be sure that the evaluation actually measures a property of the model as it would be displayed in the wild, and not a model property that is kind of that the model intends to present us with because it knows that it is basically under test and wants to deceive us. We want these evaluations to surface latent capabilities, which is an old topic, but it's still, I think, very far from solved. So for almost all the dangerous capabilities that for which we have somewhat reasonable evaluations, we know that people keep breaking those scores by just more sophisticated scaffolding. So we aren't really sure yet what the upper bound on the capabilities is. And we also don't really have a solid methodology for estimating upper bounds based on a given evaluation. We want our evaluations to be legible, which means whatever Nora means legible is. No, it means that it should be easy to communicate and transparent for every involved stakeholder. And we want them to have a wide difficulty spectrum, or as experimental physicists would say, a high dynamic range. So they should be giving us a good signal both for not so capable models, but also for very, very capable models. And finally, of course, they should be safe to implement. So we don't want to actually incur a huge risk when we just run the model evaluation itself. And finally, at the end, of course, it needs to be said that model evaluations are not the one and only solution to AI risks. Very far from that. They must clearly be combined with other tools to be effective in the first place, and also to have a chance of really substantially reducing risks. Here's some of them. So pre-deployment, on top of evaluations, we also want progress in model interpretability to tell us about maybe suspicious behavior of models that is not captured by existing evaluations. With a big question mark, maybe there's a way to get something like provable safety. So when maybe there's other approaches apart from the existing interpretability ideas that could tell us something about the properties of models that also do not rely on behavioral testing. Then on the post-deployment side, we need additional safeguards to complement what kind of security we get from evaluations. That includes model monitoring and filtering of inputs and outputs, probably other things as well. And of course, we need legal frameworks to mandate those evaluations, but also mandate any other kind of risk mitigation measures that we find useful. Other specific things that I think would help a lot is incident reporting frameworks. So similarly to what you have now in cybersecurity, where there's clear structures for how to report vulnerabilities in a safe way. We need something like that as well for AI. And of course, the international agreements to kind of have that structure on a global level. Yeah, so to finish this, these are, I think, some of the important open questions. How do we get robust evaluation methodologies? How do we evaluate the kind of more fuzzy types of risks that fall under the structural, systemic, multi-agent banner? How do we evaluate alignment? And how do we get evaluations which are robust to reception? For the future, I think this means that we actually need more research in evaluation methodologies, maybe much more than in specific evaluations. So I think there needs to be really more foundational work. Maybe also in theories of impact, so really understanding what kind of evaluations would make a big impact. There also, I think, needs to be not only fundamental research, but also engineering funded to make high quality evaluations widely accessible, because currently it's actually not the case that there is such a standard test suite that covers like the most important risks that is easily applicable. It's very hard to actually do a wide range of evaluations for your model. So I think this needs to be provided as kind of a public infrastructure. And we should probably also fund re-evaluation of existing evaluations, because we don't understand well enough how robust these are and how reliable the results are that we have. If you're a researcher, then I think you should just do the research and engineering that I've mentioned above, specifically on the methodology side, and also get involved in policy discussions so that funds are directed in reasonable research directions. Other things you can do next. One, if you're interested in playing around with evaluations yourself, there's a chance to do that at one of our next hackathons, which is coming up on the 24th of November. I hope that maybe some people here or in the vicinity of PIBBSS and ACS will be interested to try their hands and play with new evaluation ideas. And there's a bunch of resources. Of course, there's much more than that. I found the Entropic one quite interesting. It's like a short blog post that explains the problems they found, even with like their engineering budget and engineering expertise when trying to like do really systematic evaluations. So I think that's a pretty good read to get a view of where we stand currently. And yeah, this is it. Sorry for taking quite a bit of time. I hope it wasn't too long. I'm very happy to take any questions or have inputs from you.
Thanks, Jason. That was great research, very interesting. Yeah, so I'll field questions now. Just raise your hand. I think there's a raise hand function here. Or just go ahead and speak.
We have a question here.
Hey, thanks for the presentation. So my question is, what do you think we will need to have evaluations with false negative rate that is very close or like approaching zero? Because for now it seems like what evaluations give us is that they give us very strong evidence that the model can do something. But how can we evaluate that the model can't do something, or that it is not misaligned in some specific way, which it might hide via deception?
Yeah, I think the short answer is that I don't know either. I don't think there's currently a good answer to this. I think maybe mechanistic interpretability could give us some answers. So if our understanding of like model internals becomes good enough, there might be a reasonable argument that, let's say, if a certain concept is not even represented in some sense inside the model, maybe it cannot actually do anything that relies on that. So if the model, I don't know, doesn't have a concept of, and then this is not an applicable example, because this is probably not true for Frontier models, but if the model doesn't have a concept of like manipulation or so, maybe it cannot do that. Other than future, like banking on future insights in mechanistic interpretability, I think the best I think we can do is probably look at red teaming from other disciplines, so mostly cybersecurity, and see what people do there to kind of, because it's, I think, a similar situation. You don't really know you don't really know what kind of things can happen with your system, and there's no real methodology for proving that your system is safe against certain attacks. So what you do is like you devise methods to make attacks more likely in a controlled environment. So you set up honeypots to draw like attackers in. Something like that can be done for AIs maybe as well. It clearly does not solve like the full deception issue. Like a sufficiently strong model would probably recognize that it's being tested still. I don't know. Yeah, if anyone has good ideas there, I'd be super happy to hear them. I don't think there is a clear answer yet.
Okay, thanks.
I have a quick follow-up thought. So I think I'm pretty pessimistic that mechanistic interpretability is getting us a long way in that direction. I think largely because I think like in some important sense, like what we mean by capability or what we're worried about is just not fully determined by the model's internals. So like a virus doesn't have a model of humanity and can still in principle wipe out humanity or something like that. Like the actual effects on the world are not determined solely by the model internals. And I think for that reason, I'm I don't know, fairly pessimistic. I don't know, might be biased. I'm curious for like, other thoughts on why I'm sure maybe be less pessimistic. But I do, on the other hand, the second thing you said, I do find that I think there's some hope in that direction, especially if it's like paired up with like setups that allow us to iterate more, like so yeah, like sort of like security mindset, but then paired with what can we do to make stuff more iterable. I think that could get us a long way, but I think that probably involves thinking harder about alternative AI paradigms or something. Like I think sort of in the deep learning black box world, I'm just like, well, it doesn't look great. But also we could build AI in different ways or something like that. That's my 2 cents.
Yeah, I think I agree with the second point for sure. Yeah, iteration on this is pretty important, and I think it's good that like when we don't have the systematic solution, it's pretty good to be open about this and acknowledge it and just go for whatever, like go for as much interaction with the model as possible. Try to learn as much, like with a pretty open mind, and be open to be surprised. Seems definitely good. Probably playing with other methodologies or like other machine learning frameworks could help us to like generate new insights. For the first point, yeah, I think I agree with the fundamental point that it's not necessary for a model to have like a super advanced capability to actually cause great harm. But for some types of risks, I think this seems to be necessary. And so I think we will not find like a one size fits all solution to like reduce AI risks. And we probably need to kind of eat away at the risk wherever we can. So I don't think investing in evaluations should be weighed against thinking about structural risks, for example. Is definitely also needed. But I think for some of the non-structural risks, there is a chance that like evaluations can significantly reduce them. And I think also maybe mechanistic interpretability has a role to play there, if that makes sense.
Yeah, it does. It does. I agree. I had maybe one more quick thought, and then I'm done. On the policy interface, I think there might be, yeah, I liked some of the points you said, and I wanted to add the thought that I think there might be promising setups where we like potentially get like AI companies in the position of having to have good insurance. Like there being sort of like liability setups that like they would have to pay for things going wrong, and then making it in their interest to actually, for example, insure for these risks. And now you have like an additional sort of external agent, like the insurer, that is like has the model evaluation been like kind of sufficiently careful that I'm like willing to insure you for these risks or something. And I think that adds like game theoretically or sort of like market setup wise, like a non-trivial extra sort of pressure towards people being careful or firms being careful.
Yeah, totally. Well, that makes a lot of sense. I think it does make sense to rely on more than the pride of some academics in their own methodologies as a safeguard, and probably like strong financial incentives are definitely a good idea. Yeah.
You guys have other questions? Cool. No more questions in the room.
Questions from anyone else outside of Nora's room? So I had some follow-up thoughts on Nora's comment. I don't know if there's a question here. But yeah, I guess from my understanding of how mechanistic interpretability is often used in AI alignment, I think it's kind of a catch-all term for any attempt to sort of open the black box. And in like biology, the philosophy of biology, but also psychology, there's often a distinction made between mechanistic interpretations and like other sorts of, or mechanistic explanations and other sorts of explanations. So a big contrast class is like dynamical systems explanations. So in dynamical systems explanations, you might still be trying to get some idea for what's going on internally, but you're taking a systems approach, which I think, corresponds to a little bit of Nora's worries, right? That we don't, like if you think about a virus, if you want to think about the impact of a virus on a whole organism, you're not just going to look at sort of the mechanism of the virus, you're going to look at how the virus is like dynamically coupled with cells with which it's interacting, and so on. And so I guess I'm wondering, just from your experience, do you encounter this sort of distinction? Because I think that sometimes approaches that are looking for dynamical couplings between something that's going on inside of a model and external factors, whether it's the training data, whether it's the prompts that we're using, can often like be labeled under the mechanistic interpretability sort of banner, but are doing something slightly different that I think actually captures Nora's worries. But I'm a little unsure because I'm not familiar with whether or not people are doing this sort of thing in AI interpretability, but it is a common move in like systems biology and neuroscience and psychology.
Yeah, I think I mean I'm not an expert in interpretability, so I might be missing a lot of things. I haven't seen much of that. I think there is some awareness now of like data dependency and also studying trying to kind of find traces of the training data inside the model, things like that. but I think that's probably not exactly addressing Nora's point yet. So I guess my worry is like, so this is all I have to say, I think, about the state of literature. I'm not sure. The literature that I see seems to be pretty much on like the very mechanistic side. That's that. But on the point, or the connection to Nora's point, I think the thing I worry about is, would we actually be able to figure something reasonable out if we hadn't seen a virus before? Like, and is that like a feasible approach for potentially quite new types of risks? I'm not sure. I don't know if I'm explaining myself, but yeah, I wonder if there's a way to kind of devise a good structural or dynamical systems model that captures the essential properties if you haven't actually seen the type of failure that you try to prevent, which has been the case for a virus. I mean, like, we have had lots of interactions with viruses, so yeah, it would be curious if Nora has an opinion there, or you have.
Yeah, I'm not quite sure. I mean, one thing to mention is like, well, one of the ambitious proposals that exists basically involve, cool, like, let's basically just like have formal models that capture all of our scientific understanding of the world, and then we can start to like back out formal proofs from that. So like the sort of Davidat's open agency agenda, like, I think sort of an important way extent to which, like, important way in which he tries to get around some of those worries, but just like, cool, like, let's have a formal model of the world, or like all what we think are the critical forces of a given system, and then combine that with, and then be able to eventually back out proofs from that. So like, maybe that then allows you to like not have to know the risk already, because like you believe your model will like show it to you anyway. But the uncertainty bars of like where our scientific understanding is for that and how to build it are obviously kind of large. Yeah,
I think that's probably a point where I, like, just from my background, I'm naturally pessimistic. Just because like, I've tried to model systems in the lab and it's really hard actually to capture all the essential properties, because actual systems just have so many different aspects to take care of. Like, even if you think you have, I don't know, you're building an optical setup in a lab and you think you just care about how this thing interacts with the laser. It's also a thermal system that kind of moves depending on the temperature. It like interacts with like acoustic vibrations in the air. The photodetector might be sensitive to some electronic noise. I mean, this is just like random examples, but these kind of abstractions that allow us to like to write down a simple model for even such a very, very simple, I don't know, quantum optics experiment, they just break down all the time because you get just kind of crosstalk from other properties of the system that you actually didn't want to even think about, but you're just forced to do it because it's not possible to abstract it away.
Yeah.
So I'd be naturally pessimistic that this can be done on the level of like the whole world or so.
Yeah.
But, yeah.
I think the thing that is the idea in the open agency agenda is basically, yes, let's try to get over this obstacle by A, having AI systems help us do it, and by B, having models that are compositional, such that we like, there's one layer where we sort of like model this dynamic, and this other layer, but that is like mathematically compositional, such that you then can like add it up or something. I think that's like the magical steps there. It's still extremely ambitious. But yeah.
Yeah. I mean, all of this is not to say that it's per se, like, it's not, I think, illegitimate to try to model it, and it's a good idea to try it. It's probably prudent to not not solely rely on modeling, at least at the current state of knowledge.
Yep.
Yeah, but I think this is like one of my like persisting questions. If we think about AI risks, and think about like structural risks specifically, like interactions between AI systems and let's say a human economy or so. How much of the risk are we actually capturing in our models? Is it like 10% or 90%?
Yeah.
Or 0.1%? I'm not sure.
Yeah.
Any final questions from anyone else? All right. Yeah, thank you, Jason. Enjoyed that. And yeah, thanks everybody for attending. And we'll have this video posted to the YouTube channel soon.
Well, thank you,
Awesome.
Jason.
Thanks so much. Have a nice evening, everyone.
You too.
Thanks.
Bye. Bye,
Bye-bye.
Zach.
Bye. See you, Nora.